This is lesson 2.2, conditional statements. The learning targets for this lesson are that you will be able to identify, write, and analyze truth values of conditional statements, and that you'll be able to write the inverse, converse, and contrapositive of a conditional statement. So the first clip is going to cover the first learning target. The second clip will cover the second learning target. A conditional statement is a statement that has conditions. We kind of had this in lesson 2.1 when we were trying to do counterexamples, and we said that our counterexample must meet the first part of the sentence. The first part of the sentence was the conditions for whatever the problem was. But conditional statements are usually written in an if-then form. If P, if statement P, then Q, where P is the hypothesis, the conditions of a conditional statement, and Q is the conclusion, or the result, what we expect to be the result, or what follows the conditions. So, our first example, identifying parts of a conditional statement. The hypothesis almost always comes after the word if. Hypothesis should come after the word if. Hypothesis, we use P to, that's our notation for the hypothesis, and Q is our notation for the conclusion. Conclusion usually comes after the word then, except sometimes there isn't a word then, it's just a comma. And it's not always true that the hypothesis comes after the word if, so I will look at some of those examples in just a second. So we're supposed to identify the hypothesis of each and conclusion of each statement. If today is Thanksgiving, then today is Thursday. I'm going to circle the hypothesis and underline the conclusion to save time. Now in your practice, you're going to need to write these out, particularly if it's from bookwork or on an assessment. So if today is Thanksgiving, so the conditions are that today is Thanksgiving, then today is Thursday. Letter B, a number is a rational number if is not actually part of the hypothesis, it's the words that come after it. So if a number can be expressed as a fraction, then that number is a rational statement. They just wrote it in the reverse order and put the if later in the sentence. So it's a number is a rational number if it can be expressed as a fraction. This right here is the conditions for the rational number. Letter C, if today is Saturday, so today being Saturday is the conditions, then it is the weekend. It is the weekend is the conclusion. So notice that the word if and then are not actually part of the conditional statement. I mean, they're part of the conditional sentence. But the word if is not part of our hypothesis, the word then is not part of our conclusion, but rather the words that follow these signal words. Letter D, a number is divisible by 3 if it is divisible by 6. Well, you should know from the previous examples that it is divisible by 6 is the hypothesis. The number is divisible by 3 is the conclusion, even though it didn't have the word then. Example 2, writing a conditional statement. So it's important when we're writing a conditional statement that we think about what would the conditions from this sentence be, or which one is dependent on the other one. And so we're actually looking at, in terms of a Venn diagram, the subgroup should be the hypothesis. No. The subgroup should be the conclusion, and the larger group, nope, I'm wrong on that, sorry. The subgroup should be the hypothesis, the larger group should be the conclusion. So that anything that meets these conditions, everything that meets these conditions, will also result in something that meets the conditions, or not the conditions, but what meets the result of our conclusion. When you're thinking about subgroups, this means that everything that's in P is in Q. So here we have two angles that are complementary. If two angles are two angles that are complementary are acute. We're supposed to write this as an if-then. So let's see, if two angles are complementary, then they are acute, or if they are acute, then they're complementary. The more specific one, the subgroup, is complementary. And if I have complementary, they're a part of the larger group of all acute angles, whether those angles are acute or complementary or not. So this is our hypothesis being complementary. The larger group is being acute. So if two angles are complementary, then they are acute. If two angles are complementary, then they are acute. Letter B, all tarantulas are spiders. Okay, this is another way to write an if-then sentence. But again, we don't need to know all of the ways, but we do need to think about the larger group and the subgroup. Tarantulas are a specific type of spider, so those are the subgroup. The larger group is the group of all spiders. So if, and I don't want to say an animal, but we'll say an animal, that's not technically correct, is a tarantula, or maybe you say if your pet is a tarantula, then it is a spider. So here I have my subgroup being tarantulas, my larger group being spiders. If your pet is a tarantula, then it is a spider. See if you can pause the video for a minute and just try to identify the subgroup and the larger group for the next several statements. Letter C is a little tougher because it has, well, which one's a subgroup? Well, you're either, right, if you're looking at the sunset, then you're looking a specific direction. If you're looking west, you're looking a specific direction. So it turns out that watching the sunset is our hypothesis. Conclusion is looking west. And I'm going to talk to you about some structures based on this in a second, so we can tell what P and Q is in a weird case like this. So this would be if you are watching the sunset, then you are looking west. If you are watching the sunset, then you are looking west. This is a lot like, it's already written much like an if-then sentence. This implies is the word that works really well with an if-then sentence in terms of the order already being set up the way we need it. WLN students are part of the Walled Lake Consolidated School District. Well, Northern students is one group, it's a subgroup of the larger group, the district. So there's our P, there's our Q. So if someone, I'm going to say if you, are a WLN student, if you are a WLN student, then you are part of WLCSD, Walled Lake Consolidated School District. Try letters E and F. You've already identified what you think P and Q are. P is watching the football game. Watching sports is the conclusion. The hypothesis for members of the library and science members of the library is P. Science museum is Q. So you should have if you are watching a football game, then you are watching sports. And our last sentence, if you are a member of the library, then you are a member of the Science Museum. So if you are a member of the library, then you are a member of the Science Museum. So these are how we identify P and Q. Now there are some structures, there are several structures. We could either have if P, then Q. That's what we usually write our conditionals as. That's what we wrote all of these as. We could have P implies Q. You saw that twice here. We could have Q, comma, if P. We saw that above in example 1a and example 1d. There's one other one, and it's really tricky. We don't see it a lot, but sometimes we do. And that's Q, wait a second. Q only if P. No, I need to look back at it. I will make sure that you're ready for it. So, okay, we have that. You have those three structures right there that if you see the sentence written with the word implies, you should know the first part is P, the second part is Q. If it's Q, comma, if P, then it should be the conclusion's coming first, P is coming after the word if. And if P, then Q, you can identify the hypothesis and conclusion. The one that is tricky is P only if Q. And we'll talk about that in class. But basically, normally everything, the hypothesis always follows the word if, except in this unique case, which we don't see very often. The truth value of a conditional statement. We actually have a little table to help us understand this. And the truth value of a conditional statement can be determined as follows. Now, the idea is, again, the only time that we're going to be able to prove something false is, remember, to prove false, you must have a counterexample. You don't need many, just one, but you need at least one counterexample. You don't need more than one. You might have more than one, but you only need one. And that counterexample, remember, has to meet the conditions. So the counterexample must make the hypothesis true, but lead to a different conclusion. So I give some crazy examples that you will see in class, but here is a truth table. I have my P and my Q, and I have if P, then Q. That's the arrow. Oh, that's the other thing that we should go back to the front. The other way that this could be used in terms of notation is P arrow Q. P leads to Q. If P, then Q is how it's read. So I have my hypothesis, I have my conclusion, and then I have my statement. There are 4 cases that we're going to look at, so we're going to split this table into 4 boxes. If the hypothesis is something that's true, and it leads us to the conclusion always, and the conclusion is something that really exists, then the statement, as long as this leads to this and you can't find any other counterexamples, then it is a true conditional. If your hypothesis is true, but your conclusion could be false, and this is where you will have a counterexample, because your counterexample will meet the conditions of the true hypothesis and lead to a different conclusion than what was written, then you can say it's false, but you must provide a counterexample. These two students usually understand pretty clearly. They make a lot of sense to us. So I say something like, if x is even, then x plus 1 is odd. And you're like, okay, I looked for some numerical examples. Yeah, you can have a number that's even. So I put a number in for x, and it's even. If I add 1 to it every time, I'm going to get an odd number. So you say true. Then I say, if x is even, you don't have to write this down, but it's just to make sure you understand the table, then x plus 1 is prime. Well, it might be true. Let's see. We have even numbers like 2. Well, 2 plus 1 is 3, which is prime. Yay, it works. The question is, does it always work? Or is there a counterexample out there? What if I take the number 8? 8 is even. 8 plus 1 is 9. 9 is not prime. So in this particular case, this is a false conditional sentence. And the reason I can say that it's false is because I can provide my counterexample of x equals 8. Because 8 meets the conditions of the hypotenuse, but gives a different, or not hypotenuse, hypothesis, sorry, but gives a different conclusion. So these two usually make sense. Hey, Mr. Ritter, if I can think of everything possible, and this does lead to this, true, true, it's a true statement. True, false, or at least I can come up with a counterexample that makes the first part true and gives a different conclusion, that's hence the true, false, then I can say the conditional is false. Now the two that trick students, they can be a little bit tricky, is if the hypothesis is something that is never going to happen. So a false hypothesis. Now that doesn't mean that the statement is valid in terms of what they're talking about, but if it's false, then it doesn't matter whether the conclusion is something that can happen or couldn't happen. The conclusion's never going to happen as a result of that hypothesis. But even though it's not really existing, we can't actually provide a counterexample because the counterexample must meet the conditions of the hypothesis. We could say your hypothesis is invalid, your hypothesis is never going to happen, but the conditional itself would stand as true. And that's the weird case. And so, for example, if a unicorn lives in our classroom, then we eat peanut butter and jelly for lunch. Well, some of us might eat peanut butter and jelly for lunch. That would be true. Some of us might have a peanut allergy, or we just don't like peanut butter and jelly, or maybe we pack something else that day. So the conclusion could be true or false. But we don't have a unicorn that lives in our classroom. So you can say, well, your conditional is invalid because your hypothesis is false. That's an accurate statement. But the conditional, if a unicorn lives in our classroom, then we eat peanut butter and jelly for lunch, we can't prove that conditional false other than to say, well, your premise is false, so that is a ridiculous conditional. But it would lead to a true statement. Because we don't know, maybe if we did live in a world where a unicorn lived in our classroom, maybe everybody would eat peanut butter and jelly for lunch. Probably not. But if we did, if that happened, then we could prove that it was false. We'd have a counterexample. So that's the part that's tricky. The key thing that you need to know going forward is that if you're going to say something is false, you must provide a counterexample that meets the conditions of the hypothesis. Otherwise, you can't say that it's false. So analyzing the truth value of a conditional statement. Determine each conditional is true. If false, give a counterexample. If the month is August, then next month is September. Okay, so we're going to assume for these ones that we're looking at right now that the hypothesis is true. We're kind of going to negate what I just talked about because I'm not going to be giving you crazy arguments like that in here. So if it is August, if this month were August, would the next month be September? Yes, that would be true. If I weren't ignoring this part, and I didn't mean to scribble that out there, if I weren't ignoring this part, this month is not August, right? Then the next month is It's not September, next month is December. So it's still a true statement, even if I look at it from this argument down here. If an angle is obtuse, so we're assuming we have an obtuse angle, all angles that we look at must meet this condition, then it has the measure of 100 degrees. Well, that's false, because you could have an angle of 91 degrees, or 101, or 170. Anything greater than 90 but less than or equal to 180. I don't need to give the definition of it, I just need to give one counterexample. And that's a good counterexample. It meets the definition of an obtuse angle, but it is not meeting the conclusion. If 3 points form the vertices of a triangle, then they lie on the same plane. Okay, if they form, well, a triangle is a two-dimensional surface, and that two-dimensional surface makes a plane, and they would lie on the plane, those 3 points together. So this is a true conditional statement, because when you have this, it will always lead to that conclusion. And if a number is divisible by 2, then it is a perfect square. Well, 4 is, but I don't want it to be. Let's see, what about 8? 8 divided by 2 is 4, so yes, it's divisible by 2, but 8 is not a perfect square. So I can say false, and my counterexample is 8. This concludes clip 1 for 2.2. Stay tuned for clip 2 to learn how to write converse, inverse, and contrapositive.